May 15, 1943, Kummersdorf Proving Ground, 40 kilometers south of Berlin. Oberingenieur Klaus Müller stepped out of his staff car, and the first thing that struck him was how utterly wrong the American tank looked. The M4 Sherman medium tank sat on the test track like a metal box someone had forgotten to shape properly. After 15 years designing tanks for the Third Reich, creating the suspension systems for the Panzer IV, consulting on the Tiger's transmission, reviewing every schematic for the Panther's revolutionary sloped armor, Müller knew excellence when he saw it. This was the opposite of excellence. The Sherman's vertical hull sides presented perfect shot traps for any competent gunner. The riveted construction looked like something from the last war, primitive compared to the welded armor of modern German tanks. Its silhouette towered nearly 10 feet tall, a metal lighthouse that would be visible from kilometers away across any battlefield. Through the open hatches, Müller could see crew compartments so cramped they seemed designed to torture rather than protect soldiers. But what offended him most was the engine. Intelligence reports confirmed it. The Americans had installed a gasoline power plant in a combat vehicle. Every German engineer knew diesel was superior, safer, more efficient, less prone to catastrophic fires. Yet here sat this American monstrosity, a rolling incendiary bomb waiting to immolate its crew. "This is what we're supposed to test?" Heinrich Weber, Müller's assistant and former student, asked incredulously. Weber had graduated top of his class at the Technical University of Berlin in 1938, joining Kummersdorf's elite evaluation team at age 24. He stood beside the Sherman, notebook in hand, cataloging flaws with visible disdain. "It looks like they bolted armor plates to a tractor and called it a tank." Müller walked slowly around the vehicle, his engineer's eye dissecting every perceived inadequacy. The tracks, too narrow, creating excessive ground pressure. The suspension, simple vertical volet springs that looked 20 years out of date compared to German interleaved road wheels. The gun, a 75mm M3 weapon, was adequate but unremarkable. Intelligence reports indicated maximum armor thickness of just 51 mm on the hull front, increasing to 76 mm on the gun mantlet, pathetically thin compared to the Tiger's 100 mm or the Panther's effective 140 mm of sloped protection. "The troops call them Tommykochers," Weber continued, using the nickname German tankers had coined after fighting Shermans in Tunisia. Tommykochers because the gasoline-powered tanks allegedly burst into flames when penetrated. "Our boys in Africa said one good hit and they brew up like kettles. Easy kills." Müller made careful notes on his clipboard. The test program, ordered directly by the Waffenprüfamt, the weapons testing office, would run 2 weeks. They would evaluate mobility, mechanical reliability, armor protection, and firepower. Then they would write a comprehensive report explaining, with technical precision and irrefutable data, why German tank design philosophy represented the pinnacle of armored warfare and American tanks were evolutionary dead ends. The morning sun climbed higher, warming the concrete test pad. A light breeze carried the smell of machine oil and cordite from the firing ranges. Müller paused beside the Sherman's left track, studying the rubber-shod steel links. Simple, crude even, but something nagged at him, a detail in the intelligence reports he couldn't quite place. "Sir," Weber called from the engine deck, where he'd climbed to examine the power plant access panels. "You should see this. The engine compartment has quick-release access panels. Everything uses standard bolts and—" He paused, his voice taking on a note of confusion. "The entire engine appears to be mounted on a removable cradle." Müller frowned. "That can't be right. Check the technical intelligence file again." What Müller didn't know as he stood in that spring sunshine making dismissive notes about American engineering incompetence was that his world was about to shatter. Within 72 hours, he would file a preliminary report so disturbing that it would be immediately classified secret and sent directly to Albert Speer, Minister of Armaments and War Production. Within 2 weeks, he would write a recommendation that Germany abandon its entire approach to tank development, a recommendation that would be filed and ignored as the Reich continued its march toward mechanical excellence and strategic defeat. The revelation would not come from discovering the Sherman was a superior battle tank. It would come from something far more disturbing, the realization that the Americans had built a tank that could be mass-produced faster than Germany could destroy them, maintained by minimally trained mechanics under the worst combat conditions, and fielded in numbers that made individual tactical superiority completely irrelevant. The mathematics of industrial warfare were about to be written in a language German engineers had never learned to speak, and Klaus Müller would be the first to understand what those equations meant for the Third Reich's future. The propaganda wall meets reality. By May 1943, German military culture had constructed an elaborate mythology about American military equipment. These weren't just casual stereotypes. They were formalized doctrine taught in training schools and reinforced through official communications. American soldiers, the doctrine held, were soft urbanites and pampered farm boys who'd never known hardship. They trained in comfortable barracks with hot showers and abundant food, preparing to fight a war as if it were a sporting event, with rules and referees. Their equipment reflected this supposed weakness. Designed by engineers who'd never seen combat, built by factory workers who didn't understand warfare, operated by crews who lacked the spiritual strength and fighting determination that defined the Wehrmacht. The Sherman tank embodied these perceived American failures. It was, German tankers believed, a hastily designed machine rushed into production by a nation that understood manufacturing but not war. Its high silhouette suggested engineers who prioritized crew comfort over tactical necessity. Its gasoline engine revealed industrial laziness. Diesel was harder to manufacture but superior in combat. Its relatively thin armor indicated American unwillingness to accept the weight penalties that protection required. Afrika Korps veterans returning from Tunisia told stories that reinforced every prejudice. They described Shermans burning after single penetrating hits, their gasoline engines transforming crew compartments into crematoriums. They recounted battles where a single Tiger or Panther destroyed 5, 6, even 10 Shermans without taking damage. They spoke of American crews abandoning tanks after minor hits that German crews would have shrugged off. These stories were true as far as they went. What the stories omitted was context that would have terrified Wehrmacht High Command if anyone had bothered to analyze the data properly. Yes, German tanks destroyed Shermans at impressive ratios, but for every Sherman destroyed on Monday, 3 more appeared Tuesday. For every German tank awaiting parts and repair, sometimes for weeks, a damaged Sherman returned to action within hours. The individual tactical victories that German crews won were becoming meaningless in an attritional war. They were losing without realizing it. Oberst Heinrich von Luttwitz, a Panzer Regiment commander who'd survived from Poland through Africa, understood this in a way most of his peers didn't. In his private diary, discovered after his death in 1945, he wrote in March 1943, "We are the finest tank crews in the world, driving the finest tanks, winning every engagement, and we are dying anyway, not from defeat but from exhaustion. We kill 5 and they send 10. We kill 10 and they send 20. Meanwhile, Hans waits 3 weeks for a replacement transmission. Dieter's Panther has sat immobile for a month awaiting final drive parts. The Americans don't seem to have these problems. When I mentioned this to the general, he told me not to spread defeatism. But it's not defeatism, it's arithmetic. Müller arrived at Kummersdorf with his preconceptions intact, reinforced by 20 years of German technical achievement. He had watched the Wehrmacht conquer most of Europe with tanks he'd helped design. He had seen the Panther's test results, speed, armor, firepower that made it theoretically unstoppable. He had read reports about the Tiger, the most powerful tank in the world, a mobile fortress that could engage enemies at ranges where they couldn't fight back. The testing would simply confirm what everyone already knew. German engineering was superior. German tanks were superior. The Americans, for all their industrial capacity, had produced an inferior weapon because they didn't understand the art of tank design. The first test was scheduled for 800 hours on May 16th, a basic evaluation of automotive performance. A German crew trained on the Sherman's controls over the previous week would drive a predetermined 120-kilometer course, measuring fuel consumption, maximum speed, cross-country mobility, and mechanical reliability. This was Kummersdorf's standard evaluation, the same test used for every tank. German tanks regularly completed it, though rarely without requiring some adjustment and minor maintenance. Müller watched as the German crew, carefully selected for their experience and professionalism, climbed into the Sherman. Oberfeldwebel Kurt Schneider, the test driver, had operated every tank in German inventory. If anyone could expose the Sherman's weaknesses, it was Schneider. The Sherman's Continental R975 radial engine, a 9-cylinder, air-cooled gasoline power plant, producing 400 horsepower, rumbled to life at 0757 hours. The sound was different from German inline engines, a deep, steady throb rather than the higher-pitched whine of the Maybach power plants. Through the morning mist, the tank rolled toward the test course entrance, its tracks clanking rhythmically on the concrete. Müller checked his stopwatch. Weber stood ready with binoculars and the course observation log. 3 other engineers positioned themselves at key checkpoints along the route. What happened over the next 8 hours would begin the systematic destruction of every assumption Klaus Müller held about tank design. And though he didn't yet realize it, every assumption about how modern industrial wars would be fought and won. The first shock: reliability that defied understanding. The Sherman completed the 120-kilometer course in 4 hours and 37 minutes, maintaining an average speed that actually exceeded the Panzer IV's performance on identical terrain. This alone was noteworthy. The Panzer IV was Germany's main battle tank, refined through years of combat. But the Sherman's speed wasn't what stunned the evaluation team. What stunned them was what didn't happen during the run. 0 mechanical failures, 0 required adjustments, 0 fluid leaks, 0 track problems, 0 transmission issues, 0 engine anomalies, 0 electrical faults, 0 suspension damage. Müller stood at checkpoint 3, watching through binoculars as the Sherman splashed through the water obstacle, a muddy ford designed to test engine reliability and sealing. German tanks frequently experienced problems here. Water intrusion caused electrical shorts. Mud clogged air filters. The thermal shock of cold water hitting hot engines sometimes cracked cylinder heads. The Sherman drove through as if the obstacle didn't exist. The engine never hesitated, never stumbled. It emerged from the far side with water streaming from its hull, accelerated smoothly up the exit ramp, and continued toward the next checkpoint without pause. At checkpoint 5, the Sherman climbed the maximum grade obstacle, a dirt embankment inclined at 60%, the steepest gradient most tanks could handle. This obstacle broke transmissions, stalled engines, and threw tracks. Müller watched the Sherman approach, expecting to see Schneider carefully select the proper gear, balance engine speed against traction, nurse the tank up the slope through skill and experience. Instead, Schneider simply pointed the Sherman at the embankment and drove up it. The transmission shifted smoothly through the gears without grinding. The engine maintained steady power without laboring. The tracks bit into the dirt without slipping. At the top, the Sherman didn't hesitate or wallow. It simply crested the obstacle and continued. Weber, monitoring from the command post, radioed Müller with confusion evident in his voice. "Sir, Schneider reports all systems operating normally. Engine temperature normal, oil pressure stable, no warning indicators. He says it's easier than driving a Panzer IV." When the Sherman returned to the test pad after completing the full course, Müller walked around it slowly, looking for signs of stress or damage. The tracks showed normal wear patterns. The suspension components showed no signs of strain. The engine, which should have been radiating heat after 4 hours of hard running, was warm but not excessively hot. The air-cooled radial dispersed thermal energy efficiently, eliminating the overheating issues that plagued German liquid-cooled engines. Schneider climbed out, removing his leather helmet. "Sir, I don't understand. According to my experience, we should have needed at least 2 track adjustments. The suspension crossing those rough sections should have required checking. The engine temperature approaching the maximum grade obstacle should have spiked. None of that happened. Everything just worked." Müller checked the maintenance log Schneider handed him. The entries were minimal. Pre-run inspection, all systems normal. Mid-run observation, all systems normal. Post-run inspection, all systems normal. No adjustments performed, no corrections made, no issues identified. "Run it again," Müller ordered. "Same course, no maintenance between runs." Weber looked at him questioningly. "Sir, the test protocol requires full inspection and adjustment between runs. We need to check track tension, fluid levels, examine—" "I said run it again," Müller interrupted. "I want to know if the first run was an anomaly or if this machine is actually this reliable." The second run began at 13:45 hours. Müller observed from different checkpoints this time, focusing on areas where German tanks typically showed weaknesses. At the rough cross-country section, where interleaved German road wheels frequently accumulated mud that froze suspensions, the Sherman's simple vertical volute springs absorbed impacts and shed debris without issue. At the high-speed straightaway, where German tanks sometimes threw tracks due to the stress of rapid acceleration, the Sherman's tracks remained firmly in place. At the obstacle course, where complex maneuvers stressed steering systems, the Sherman's controlled differential steering worked smoothly without the binding that plagued German systems. The Sherman completed the second run in 4 hours and 41 minutes, 4 minutes slower than the first run, well within normal variance. Schneider reported 0 mechanical issues. All controls operated normally. The engine maintained consistent power. No warning indicators showed problems. Müller felt something he'd never experienced in 15 years of tank evaluation, a cold knot of unease forming in his stomach. This wasn't supposed to happen. Tanks didn't perform perfectly on back-to-back test runs. There were always minor issues, adjustments needed, components checked, fluids topped off. That was simply the nature of complex mechanical systems operating under stress. Yet here sat this ungainly American machine, having just completed 240 kilometers of punishing testing, and it looked ready to run another 240 kilometers without complaint. "Prepare for the extended reliability test," Müller instructed, his voice tight. 500 kilometers, continuous operation except for refueling stops. I want to know where this thing breaks." Weber hesitated. "Sir, that's beyond our standard protocol. The Panthers that went through extended testing all required significant maintenance. The Tigers—" "I know what happened to the Tigers," Müller snapped. "That's why I want to see what happens to this." He gestured at the Sherman with barely concealed frustration. "Start the test tomorrow morning. I'm going to review every piece of technical intelligence we have on American tank production. Something doesn't add up." That evening, Müller sat in his office with the intelligence files spread across his desk. The documents painted a picture that didn't match what he'd witnessed on the test track. According to captured American technical manuals, the Sherman was a relatively simple design. Nothing revolutionary, nothing that suggested exceptional performance. Yet the test results indicated reliability that exceeded anything in German inventory. He found a notation in one intelligence report that gave him pause. American tank production appears to emphasize interchangeability and ease of maintenance rather than maximum performance specifications. Multiple manufacturers produce identical components. Spare parts availability reported as excellent across all theaters. Müller read the sentence 3 times. Interchangeability, ease of maintenance, spare parts availability. These weren't typically considered primary design criteria for combat vehicles. German tanks prioritized performance, armor protection, gun power, mobility. Maintenance was secondary, something to be addressed by trained mechanics and well-supplied repair units. What if the Americans had approached the problem differently? What if they'd designed a tank that prioritized staying operational over achieving maximum specifications? What if reliability itself was a combat capability more important than any individual performance metric? Müller pulled out a calculator and began running numbers. The Sherman's test performance suggested it could operate for extended periods with minimal maintenance. If that held true in combat conditions, American tank units could maintain much higher operational readiness rates than German units. Higher operational readiness meant more tanks available for combat at any given time. More available tanks meant numerical superiority, even without superior production numbers, though intelligence suggested American production numbers were also substantially higher. The equation that emerged suggested something Müller didn't want to accept, that Germany might be losing the tank war not because German tanks were inferior, but because German tanks were too sophisticated to maintain under combat conditions. He would spend the night reviewing files, searching for evidence that would disprove this conclusion. He wouldn't find any. The extended test, when superiority becomes survival. The extended reliability test began at dawn on May 17, 1943. The protocol was straightforward but brutal. Continuous operation for 500 kilometers with maintenance strictly limited to what a standard tank crew could perform without workshop support or specialized tools. This meant checking fluid levels, adjusting track tension if necessary, and performing basic visual inspections. No component replacement, no specialized adjustments, no mechanical repairs. German tanks typically developed issues around the 200-kilometer mark under these conditions. Nothing catastrophic usually. Bearings that needed adjustment, fuel filters that needed cleaning, track blocks that worked loose and required attention. The Tiger Y, despite its fearsome reputation and nearly impenetrable armor, was notorious for mechanical fragility. Its overlapping road wheel design accumulated mud that froze the suspension. Its transmission, overstressed by the tank's enormous weight, developed synchronization problems. The final drives, under-designed for the loads they carried, overheated and sometimes failed catastrophically. Tiger crews accepted these issues as the price of operating the world's most powerful tank. The Panther, despite being newer and theoretically more refined, suffered even worse teething problems. The Maybach HL 230 P30 engine was prone to catching fire. The final drives failed with disturbing regularity, so regularly that replacement final drives were pre-positioned at repair facilities, since field repair was nearly impossible. The interleaved road wheels, which provided excellent cross-country mobility, became maintenance nightmares when damaged. Against this baseline, Müller expected the Sherman to show its true character during extended operation. American manufacturing might produce reliable performance for short tests, but sustained operation under stress would reveal the machine's true nature. The gasoline engine would develop problems. The simple suspension would prove inadequate. Something would break. It had to break. German engineering wisdom, developed over decades and refined through years of combat, said complex machines operating under stress inevitably required maintenance and adjustment. That was simply mechanical reality. The Sherman ran 100 kilometers on the first day. Schneider reported normal operation throughout. Evening inspection revealed no issues requiring attention. The second day brought 150 kilometers, including extended cross-country operation over terrain that would have torn apart lesser machines. The Sherman's suspension absorbed punishment that should have required major repairs. Evening inspection, no issues. Day 3, 120 kilometers, including high-speed road running that should have stressed the engine and transmission to their limits. The Sherman's Continental Radial maintained steady power output. The synchro-mesh transmission, a design borrowed from automobile applications, shifted smoothly under load. Track tension required minor adjustment, the first maintenance action of the test. Time required, 15 minutes. Day 4, 130 kilometers, completing the 500-kilometer test protocol. Schneider drove the Sherman onto the test pad at 16:34 hours, shut down the engine, and climbed out with an expression Miller couldn't quite read, somewhere between professional respect and existential confusion. "Sir," Schneider reported, saluting, 500 kilometers complete. The tank operates within all specifications. No mechanical failures, no component damage. Track adjustment performed once, as noted. Fuel consumption consistent with estimates. The vehicle is ready for continued operation." Miller ordered the maintenance crew to open the engine compartment for inspection, expecting to find evidence of stress even if no failures had occurred yet. Surely the engine would show signs of wear. The transmission would have metal particles in the oil, indicating incipient gear damage. Something would justify his expectations. The engine looked almost new. Oil analysis showed wear patterns consistent with normal break-in, nothing suggesting impending failure. The transmission showed no metal particles indicating gear wear. The final drives, the component that killed Panthers with horrifying regularity, operated within specification with no signs of overheating or damage. The tracks showed even wear with no thrown blocks or damaged pins. Heinrich Weber reviewed the maintenance logs, flipping through pages with mounting disbelief. "Sir, this doesn't make sense. According to these readings, this tank could run another 500 kilometers without significant maintenance. Our Panzer I-4s require workshop time at this point, bearing adjustments, filter replacements, various mechanical checks. The Panthers would need new final drives. This..." He paused, searching for words. "This is still operating in factory-fresh condition." Miller forced himself to ask the question he'd been avoiding. "What's the maintenance requirement for our tanks after 500 kilometers of operation?" Weber consulted his reference manuals, the official Wehrmacht maintenance schedules that governed armored vehicle operations. For a Panzer IV, approximately 40 hours of scheduled maintenance, plus additional time for repairs as needed. That's with trained mechanics and proper facilities. For a Panther, closer to 60 hours, not including major component replacement. For a Tiger, he trailed off. "We recommend full workshop inspection after any extended operation. The maintenance to operation ratio approaches 1-to-1 at sustained employment." "And the Sherman?" Miller's voice was barely above a whisper. "Based on these tests, sir, perhaps 5 hours of basic checks, fluid levels, visual inspection, track tension. None of it requires specialized knowledge or tools. Any trained mechanic could perform the work. Most of it could be done by the crew themselves." Müller sat down heavily in his field chair, the clipboard forgotten in his lap. His engineer's mind, trained to analyze problems through mathematics and physics, worked through the implications. A German armored division conducting sustained operations spent nearly as much time maintaining tanks as fighting with them. Each tank required a logistics train of specialized recovery vehicles, trained mechanics, stockpiles of spare parts, workshop facilities capable of complex repairs. The support personnel outnumbered combat crews. The supply requirements were enormous, not just fuel and ammunition, but hundreds of different parts, specialized tools, technical manuals. The Sherman appeared to need almost none of this. It ran, it fought, it ran more. The maintenance requirements were so minimal that field mechanics, or even the crew themselves, could handle them. Parts were interchangeable and, apparently, plentiful. The logistics tails supporting Sherman operations would be a fraction of what German armor required. This wasn't a tank. This was a weapon system designed for a completely different type of warfare. The Americans had built a machine optimized for industrial war, designed to be expendable and replaceable, yes, but also to remain operational without the sophisticated logistics that German tanks demanded. Müller made a calculation that would haunt him for the rest of his life. A simple equation with devastating implications. German tank effectiveness. Tactical superiority X, operational availability X numbers produced. American tank effectiveness. Tactical adequacy X, very high operational availability X, enormous production numbers. Even if German tanks were tactically superior, and Müller still believed they were, the Americans had created a system where individual superiority didn't matter. They could afford to lose tanks learning how to fight effectively because more tanks would arrive tomorrow. More importantly, the tanks they already had would still be running tomorrow while German tanks sat awaiting parts and repairs. "Continue testing," Müller ordered quietly. "I want to see the engine removal and replacement procedure. And bring me every intelligence file we have on American tank production, every single one." Weber nodded, but before leaving he asked the question Müller had been avoiding. "Sir, what do we do if the Americans if they've found a different solution? One that works better than ours?" Müller didn't answer immediately. Outside, the Sherman sat on the test pad in the fading afternoon light, ugly and ungainly and utterly functional. Finally, he said, "Then we learn from it, or we lose. Those are the only options." What neither man understood yet was that by May 1943, the choice was already made. Germany lacked the industrial capacity, the resources, and increasingly, the time to build tanks the American way, even if they'd wanted to. The best Müller could do was document the truth and hope someone in the command chain would understand what it meant. They wouldn't. The engine revelation, modularity as philosophy. On May 19, 1943, the fifth day of testing, Müller ordered the procedure that would complete his understanding of American engineering philosophy, engine removal and replacement. This test would prove critical because it measured not just the Sherman's battlefield performance, but its sustainability under combat conditions. In modern warfare, tanks didn't just need to fight. They needed to be repairable when damaged, maintainable when worn, and returnable to service as quickly as possible. The German approach to tank power plants reflected traditional engineering thinking. The engine and transmission formed an integrated unit, carefully designed for optimal power transfer and mechanical efficiency. This integration produced excellent performance, but created significant maintenance challenges. On a Panther tank, removing the engine required a complex, carefully choreographed procedure. First, the entire rear deck had to be removed, a process involving dozens of bolts and careful handling to prevent damage to sensitive components. Then the engine transmission unit, weighing over 1,400 kilograms, had to be extracted using a heavy crane, capable of lifting the assembly vertically through the restricted space. The procedure required specialized tools, trained technicians, and typically 24 to 36 hours in a workshop environment. In field conditions, without proper facilities, it was nearly impossible without specialized recovery and repair units. The Tiger was worse. Its Maybach HL230 P30 engine produced 700 horsepower, a masterpiece of German engineering that required not just a crane, but a specialized transport trailer and a work crew that knew the precise sequence of disconnections. Engine removal could take 2 days of intensive labor. The complexity was justified, German engineers believed, by the Tiger's superior combat performance. The Kummersdorf maintenance crew approached the Sherman with German expectations. They anticipated a day-long project requiring specialized equipment, precise procedures, and careful documentation. The crew chief, Oberfeldwebel Ernst Krüger, had removed engines from every German tank in inventory. He knew how complex the procedure was, how many things could go wrong, how critical proper equipment and training were. What they discovered over the next 4 hours would fundamentally challenge every assumption about how tanks should be designed. Krüger began by opening the Sherman's engine deck, expecting to find the familiar complexity of an integrated power plant system. Instead, he found something that looked almost absurdly simple. The Continental R975 radial engine sat in a cradle connected to the hull by 4 large bolts, each accessible with standard wrenches, no special tools required. The transmission wasn't integrated with the engine, but existed as a separate unit with its own mounting system. "Sir," Krüger called down to Müller, who was observing from beside the tank, "this doesn't make sense. The engine is just bolted in place. There's no structural integration, no complex mounting system. It's like they designed it to be removed." "That can't be right." Müller climbed onto the engine deck to see for himself. No serious engineer would design a tank engine that way. The structural loads, the vibration damping, He stopped, staring at what he was seeing. Krüger was right. The engine sat in a simple cradle with 4 mounting points. The electrical connections used standardized plugs rather than hard-wired connections. Pull one plug, disconnect one cable. The fuel lines featured quick disconnect fittings that could be operated by hand. No tools required. The cooling system hoses had simple clamps that loosened with a screwdriver. Even the exhaust system disconnected through a spring-loaded coupling. Everything about the installation suggested one design philosophy. This engine was meant to be removed and replaced quickly, without specialized equipment, without extensive training, without workshop facilities. "Proceed with removal," Müller ordered. "Time the procedure. I want to know exactly how long this takes." Krüger assembled a 5-man crew, the same crew that had removed Panther engines, experienced mechanics who knew their work. They approached the task systematically. Disconnect electrical systems, disconnect fuel lines, disconnect cooling systems, remove mounting bolts, attach lifting cables. A portable crane, the same one used for removing tank turrets for maintenance, not requiring any specialized heavy equipment, was positioned over the Sherman's engine bay. Krüger coordinated the lift, 4 men guiding the engine as it rose smoothly out of the compartment. 3 hours and 47 minutes after beginning, the engine sat on a transport dolly beside the tank. The crew stood looking at it with expressions ranging from confusion to professional respect. "Sir," Krüger reported, "the engine is removed. No specialized tools required beyond standard wrenches and the portable crane. The procedure is straightforward enough that any trained mechanic could perform it. Realistically, a tank crew could probably manage it themselves with the proper equipment." Müller examined the now empty engine compartment. The transmission remained in place, a separate unit that could be serviced independently. The propeller shaft that connected engine to transmission featured a slip joint that handled the disconnection automatically. Everything was designed for modularity, for rapid replacement rather than complex repair. "Now install the replacement," Miller ordered. "Same crew, same equipment. I want to know if this was a fluke or if the Americans actually designed this intentionally." From the captured stores of American equipment, mechanics brought another Continental R975 engine, this one taken from a Sherman destroyed in Tunisia. The installation procedure reversed the removal. Position engine in cradle, lower into compartment, connect mounting bolts, reconnect fuel lines, reconnect electrical systems, reconnect cooling system. 4 hours and 12 minutes. A complete engine replacement in under 4 hours of work, performed by a crew who'd never done the procedure before, using standard tools and equipment available to any tank unit. For comparison, Miller knew from experience that a Panther engine replacement required a minimum of 36 hours with experienced crews, specialized equipment, and workshop facilities. A Tiger engine replacement could take 3 days. The implications crashed over Miller like a wave. The Sherman wasn't designed to be repaired in the field. It was designed to have major components swapped out like modules. A damaged engine didn't require complex diagnosis and careful repair. It required 15 minutes of diagnosis followed by 4 hours of replacement. The damaged engine could be sent to a rear echelon workshop for rebuilding while the tank returned to combat with a fresh power plant. This was industrialized warfare at a level German doctrine hadn't conceived. The Americans had designed a system where tanks were platforms for interchangeable components, where complex repairs happened in factories and simple replacement happened at the front. "Test the replacement engine," Miller ordered, though he already knew what the result would be. The Sherman with its replacement engine, an engine pulled from storage after sitting unused for 2 months, an engine from a different tank built by a different factory, ran flawlessly through a 200-kilometer test course. The engine was not just interchangeable in theory, it was genuinely plug-and-play, a concept German engineering had never seriously considered because it seemed to compromise the careful optimization that maximum performance required. Weber pulled Miller aside after reviewing the parts inventory from captured American supply dumps. His voice carried a note of barely controlled alarm. "Sir, I've been looking at the intelligence files more carefully. Every Sherman engine is identical, every single one, regardless of which factory produced the tank. Every transmission is identical, every final drive is identical, even the radios." He paused for emphasis. "Every radio in every tank is identical. The same model, the same parts, complete interchangeability across the entire production run." Miller nodded slowly, pieces falling into place with terrible clarity. "Bring me the production intelligence. I need to see how many of these they're building." What the intelligence files revealed was more disturbing than any tactical defeat on any battlefield. The Sherman was being produced not by one manufacturer, but by multiple companies operating independently, yet building identical products. The list read like a survey of American industrial capacity: Chrysler Defense Arsenal, Fisher Body Division of General Motors, Ford Motor Company, American Locomotive Company, Baldwin Locomotive Works, Federal Machine and Welder Company, Pacific Car and Foundry Company, Pressed Steel Car Company, Pullman Standard Car Manufacturing Company. These weren't just final assembly plants. They were complete production facilities building interchangeable components that could be assembled anywhere. A Sherman engine built by Continental in Detroit would fit perfectly in a hull built by Pacific Car and Foundry in Washington State. A transmission from Chrysler worked identically in a Sherman built by Ford. Every radio, every track link, every road wheel, all standardized, all interchangeable. German intelligence estimated America was producing 2,000 Sherman tanks monthly by mid-1943. This estimate, Müller would later learn, was actually conservative. Actual production peaked above 2,200 units monthly. More significantly, production rates were accelerating, not slowing. American factories were ramping up output as they optimized assembly lines and overcame initial production bottlenecks. For comparison, Germany's entire tank and assault gun production was approximately 500 units monthly. Panthers, Tigers, Panzer Vs, Stu G3s, all variants combined. Even at maximum theoretical production, Germany couldn't match American output of just the Sherman, let alone total Allied armor production. But the numbers were actually worse than they appeared. German production figures represented tanks rolling off assembly lines. They said nothing about how many of those tanks remained operational after a month of service, or how many could be maintained under combat conditions, or how many could be repaired and returned to service after damage. Müller spent that evening with his calculator, working through mathematics that grew more disturbing with every equation. If American Sherman operational readiness averaged 85%, a conservative estimate based on observed reliability, and German operational readiness averaged 60%, an optimistic estimate considering maintenance requirements, then 2,000 American tanks per month translated to 1,700 operational tanks monthly, while 500 German tanks translated to 300 operational tanks. The apparent 4-1 production advantage was actually closer to 6.1 in operational terms, but even that understated reality. German tanks destroyed in combat often couldn't be recovered or repaired due to battlefield conditions. The Sherman's modular design meant even catastrophically damaged tanks could have components salvaged and reused. A Sherman with a destroyed engine but intact hull could receive a new engine and return to service. A Panther with final drive failure might sit immobilized until overrun by enemy forces. The equation that emerged was stark. America could replace combat losses faster than Germany could inflict them, while maintaining higher operational readiness across their entire tank force. This wasn't just a production advantage. It was a philosophical difference in how war itself was conceptualized. The Germans built weapons. The Americans built weapons systems. The Germans designed for excellence. The Americans designed for sustainability. The Germans optimized for performance. The Americans optimized for logistics. And in a total war of industrial attrition, logistics trumped performance every single time. Müller closed his notebook and stared at the equations covering the pages. These weren't just numbers. They were the mathematical proof that Germany was losing the war in ways that had nothing to do with battlefield tactics or soldier courage. Germany was being defeated by slide rules and assembly lines, by American engineers who understood that adequate weapons produced in overwhelming numbers would always defeat excellent weapons produced in limited quantities. He would include all of this in his final report. He would explain in technical detail why the Sherman represented a fundamental reconceptualization of armored warfare. He would recommend that Germany immediately abandon its approach to tank development and attempt to copy American design philosophy. The report would be filed and forgotten. Germany would continue building Tigers and Panthers, magnificent weapons that couldn't be produced fast enough, couldn't be maintained under combat conditions, and couldn't be replaced when destroyed. The Reich would drive itself to defeat in machines that represented the pinnacle of technical achievement and the nadir of strategic thinking. But that night, sitting alone in his office with equations that predicted the future, Klaus Müller understood with perfect clarity that Germany had already lost the war, not on any battlefield, but in the design studios and factories where tanks were conceived and built. The Americans had won the war before the first Sherman ever fired a shot in anger. They'd won it by understanding that in modern industrial warfare, the side that could produce more adequate weapons faster would always defeat the side that produced fewer excellent weapons slowly. It was a lesson Germany would never learn in time to matter.